Okay, so I'm going to start the class now. So those are the important things I need to highlight before starting the class today. Okay, so let's begin. I'm going to put this one into full screen mode. Okay, so let's go to the outline of the class today. So this is the outline of class today. We will define what is the event means, and then we discuss how to find the probability of an event, and then we discuss axioms of probability concept. Okay. Okay. In short, event is a subset of the sample space. So if you find, you know how to find the sample space now. So after you find in the sample space, your event is going to be the subset of that sample space. I will discuss a few examples later. Before discussing the examples, I want to show you how to denote it. So we can denote events by capital English letters. Okay. So in this class, if you see capital English letter means according to the context, most of the time it will be an event. So event should be defined first, and we will use capital letters to denote events. Okay, so this is another definition for events. In another way, we can say event is a set of all possible outcome of the random experiment. So in that case, omega, the sample space also an event. Okay, so let's see a few example, a simple example. Suppose as an example, we are tossing a coin twice. Okay, so let's write down the sample space for this problem, for this experiment. So this random experiment has sample space something like this. It can be head in both coins, both tossings, or it can be head in first tossing and tail in the second tossing, or tail in the first tossing, head in the second tossing, or it can be both tosses are tails. Okay, so those are the possible, all possible outcomes. So that's why it is the sample space here. Okay, so now let's define an event, which is A, is defined as exactly one head. Okay, so we can list outcomes in A like this. Within the curly bracket, we can list all the outcome that match with the definition of A. So A means the exactly one head. So these are the two possible outcomes for A. Okay, so can you see this A is a subset of omega? Okay, in other words, we can define or show this one. A is a subset of omega. So this is the mathematical notation for subset. Okay, so this is the mathematical notation for subset. So this says A is a subset of omega. Okay, so hopefully that makes sense. What is the meaning of event? So event in simply means a subset of sample space. Okay, so now after defining events, we should consider some fundamental operations on events. So the first operation is complement of an event. Okay, so the complement of an event is values. Those are not in A. Okay. So this is how we can mathematically define complement of any event A. But you don't want to memorize this one. Okay, so you don't want to memorize this one. So, but I will explain what this means. Okay, so this is how we can denote A complement. A superscript C means A complement. Or we can say this one has A prime. Okay, A prime or A C means the A complement. So this means all omegas in, so this is simple omega. And this is the lowercase omega. So that's mean all lowercase omegas in the sample space, those are not in event A. Okay, so we can visualize this one. So that's the important part. Okay, so try to understand the visualizing part. Okay, I'm going to visualize this complement part. So in Venn diagram, we can denote the sample space using a square or a rectangle, and we can use circles to denote events. Okay, so this is event A. Okay, okay, I will write down A outside of the square. So this is A. So if I color the outside of this A, so this gold color part or the orange color part is belongs to, this part is belongs to A complement. Okay, so blue color circle is for A, and this gold color shaded area or stripped area is the A complement. Okay, so any item, any outcome in this area is goes to the A complement or A complement. Okay. Okay, so we will discuss more examples later because there are a few more operations we need to discuss first. Okay, so the second types of event operations are union. So again, we can define it or we can express it in mathematical notation first. So I will explain that first and then show it, I visualize it. Okay, so we can denote it by A union B as the notation U. Okay, A union B means all omegas in large omega, so the sample space, that omega must stay in A or B. Okay, or B. It can be either A or B or both. Okay, this omega can be neither A, either B or both. Okay, so let's visualize this one. Okay, so this is how we can visualize this one. This is A, event A, and this is event B, and this is omega. And I'm going to shade the region that is belongs to A union B. So these are the shaded region is the A union B. Okay. So any item in A or B or both, these are the common region. So these omegas can be in any of these three places. So then we say this A union B. And the last thing is intersection. Okay. So intersection we will denote it by AN, and the word is AND. Okay. So in when it is union, the keyword is O. When it is intersection, the keyword is AND, A and B. So A and B means all omegas. Here, all omegas. In the large omega means all omegas in the sample space. And this omega must stay in A and B. So it should be, omega should be in both A and B. Okay, so that's mean the common region. Okay, so let's visualize this A intersection B. Okay, so this is my omega, and this is my A and B. Now I'm going to shade the region for A union B, A intersection B, sorry, A intersection B. So this is the A intersection B common area, and this is the A union B. Okay. Now let's discuss another example to understand these operations further. Okay. So please let me know if you have any questions. Okay. Please contact me if you have any questions. Okay. So tossing a coin 3 times. So the example is tossing a coin 3 times. If we define two events are getting a head on the second toss, getting exactly 2 heads. So A says getting head on the second toss. B said getting exactly 2 heads. It doesn't matter the position. Okay, so let's start with write down the sample space. Okay, so tossing 3 coins at once. So here you can get head in the first coin, head in the second coin, and head in the third coin. Or you can get head in first 2 coins and tail in the third coin. Head in first coin, tail in the second coin, and head in the third coin. Tail in the first coin, and head in the 2 and 3 coins respectively. So these are the possible outcomes with one tail. So now let's start with 2 tails. First one is head and the last 2 is tails. Or first one is tail and last 2 head and tail. And first 2 tails and last 1 head and all 3 tails. So these are the all possibilities you can get when you are tossing 3 coins at once. Okay. Now A says getting a head on the second toss. Okay, so A getting a head on the second toss. So in this case, we have to pick the corresponding outcomes that match with description of A. So here, second toss is head. Second toss is head. So this has second toss head. This one, second toss is head. So we are only focusing on second toss. If it is head, we can pick it to the event A. Second toss is not head. Second toss is head. Second toss is not head. Head. Second toss is not head. Not head. So there are 4 outcomes that those are matched with the description of A. So here A is going to be H, 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 T, T, H, H, T, H, T. Okay. And now I'm going to use different color to denote B. Okay, so B. So now B is getting exactly 2 heads. So we don't care about the position. We only count how many heads there. So if it is exactly 2 heads, we will pick them to B. So here we have 2 heads, 2 heads, 2 heads, no 2 heads, no 2 heads, no 2 heads, and 0 heads. This is not exactly 2. Okay. So here we have to get exactly 2 heads. So there are only 3 outcomes. Exactly 2 heads. Okay, so that's how you can write down the items in a event. Now let's find out A complement, B complement, A union B, and A intersection B. Okay. Now let's find A complement and B complement. A complement means all items in omega, but those are not in A. Okay, so not in A. So this is in A, this is in A, this is not in A, so we can get it into A complement. and this is in A, so we don't go to get it for, we are not going to write down in under the A complement. So this is not in A, so we have to write it under the A complement. And this is not in A. And finally, the last item, TTT. So these are the items not in A. So these are A, not in A. Similarly, let's write down B complement. So B complement means the cross process in here. So H and HTT, HTHT, EHT, TTH, and finally TT. Okay, so now let's write down item in A union B. Okay, so A union B means items in A or B or both. Okay, so here HH in A, so we have write HHH. Only look at A and B and write down the items in A, B or both in AB. Okay, so we will write down one item only once. Okay, we are not going to repeat if there are more than one item in common items. Okay, so we are not going to repeat. So H, we got into A union B. HHT, it is in both here. It is in both A and B, so we write it at once. Okay, HHT. And the next one is THH. THH also in both sets, but we will write down it once. And THT. Okay, so we write down HH, HHT, THH, THT, and so that's mean we write down this one. We write down this one. Only remaining one is HTH. So these are the items in A union B. So items in A, B, or either A or B. Okay, so the last one, A intersection B. So A intersection B are the common ones. Okay, so here the common ones are these two. So we will write once and these two. So we will write down once. So this. So it is H, H, T, T, H, H. Okay, so we discussed all three main event operations. Okay, so if you have any questions, please send me an email or visit my office hours on Thursday and Tuesday from 9 to 12. Okay. Okay, so I hope you got the idea. Okay, so now let's continue to understand more concepts related with events operations. Okay, so now we can extend these operations for what we have already learned into more than one or more than two events. So specifically union and intersection. We can extend this one into any number of events in a sample space. Okay, so suppose A1 to AM. So A1 to AM are events, then we can extend this one. Okay, so here we have M number of events. So here M number of events. And this means, so idea of this one is A1 union A2 union A3 union all the way to union of M. So the union of all this M number of events is defined like this. Okay. So here it says omega in large omega, and this little omega should stay at least one of these sub events, one of this event A1 to A. Okay, so that's why it says omega should in An for some n, okay. Okay. So these are the outcomes. Outcomes in omega such that outcome should stay at least one n in the m number of events. Okay, so similarly we can write down the intersection for m number of events. So here A1 intersection A2 intersection A3 intersection all the way to intersection of A. So that's the meaning of this part. Okay. So this is same as outcomes. So here it says outcomes in sample space such that this omega should stay all of the all of these events, m events. Okay, so this omega should stay in all m number of events. Okay, so that's how we can extend this one into m number of events. And if there are infinitely many number of events, still we can extend this one into infinitely many number of events. That's the benefit of, that's another benefit of these two operations. We can calculate intersection and union for infinitely many number of events in a sample space. So in the infinite, we will denote using 3 dots in this class. So A1, A2, and 3 dot means it is continue up to the infinity. So here we have infinite number of events in sample space omega. Okay, so first we can define the union for infinitely many number of events. So here this means A1 union A2 union dot 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 is continue up to the infinity, and the definition is still the same. So omega in outcomes in omega such that omega should stay at least one of the event A1 to infinity of the events. Okay. Similarly, we can extend the idea of intersection into infinitely many number of events. Okay, so this means outcomes in omega sample space such that all the, so this line means such that all omega should stay in the all of these events. Okay, so that's the end of extending this one into higher number of events. But in this class, you will get maximum 3 events to find union and intersection. Okay, but we can extend that one into infinitely many number of events. Okay, so the next we will talk about more terminologies we will use in this class. More terminologies, mathematical terminologies we will use in this class. An event A is containing in B if and okay. So first terminology, if every outcome of omega is also in B, so we write a subset of B. So we discussed this sign already. This is a subset. So this is a subset. So this is A is a subset of B. So we can visualize this one. So suppose we have the sample space omega, and we have one event called B, and inside B we have event A. This is the event A. So can you see event A is contained in the B. So A is containing inside the B. So A is living inside the B. So if this happen, then if every outcome of omega in A, so any outcome in this event A is also in B, because A is inside B. Okay, so this is the event A. So any outcome in this shaded region is in B as well. Okay, so that's called subset or sub event. So event of an event. Okay, so the next one is equality of two events. So if you have two events and we want to consider the equality of two events, so then it should happen both of these. It should meet both of these conditions. Okay, it should be A subset of B and B subset of A. Okay, so in this point, we are discussing about how A and B two events are equal. It should meet if this happen, if and only if A subset of B and B subset of A. So let's visualize this situation. So I'm going to use blue color to show event A. And red color to show event B. So event B also on the same edge. Okay, same edge here. This is B. So A is on B, B is on A. So that's why it is equal. So that's how two events can be equal each other. Okay, so the next terminology we should know is the null set. So omega denote the entire sample space, and this notation in mathematically we say this is pi phi. Sorry, it's not phi, it's phi. So this is phi. The set with no outcomes are with the event. Okay, so this is also known as empty event. Okay, so the next one is disjoint events. So if there are no common outcomes in two events A and B, so then we say A and B are two disjoint events. So we can denote that one like this. This is event A and this is event B. There's no common area for A and B, so that's why intersection is a null or empty set. Okay, so it is null set or empty set. So we can say this is null or empty set. So no common outcome, so that's why it is null. Okay, so the next concept is called pairwise disjoint events. Okay. So if you consider pair, so I'm going to visualize it. Okay, first. I'm going to visualize it 2 times. Okay, so I draw 3 events A, B, and C here, and 3 more events here, A, B, C. So here we can see A and B are disjoint. And A and C are also disjoint, but D and C are not disjoint. So that's mean A, B, C are not pairwise disjoint. So, but if you consider this one, A, B is disjoint, B, C disjoint, and A, C also disjoint. So in this case, A, B, and C are pairwise disjoint events. So A, B, C are pairwise disjoint events. Okay, so that's the idea of here. That's the idea of pairwise disjoints, and here we can define this one into infinitely many number of events. If it is pairwise disjoint, or the another word we can use is mutually exclusive if AI intersection of AJ is a null set for each I and J, those are not equal. Okay, so that's how we can show it in mathematically for the pairwise disjoint, and this is the idea. Okay, so if a set is pairwise disjoint means if you consider any pair, those are disjoint. Okay. And the last terminology is exhaustive event. So if the collection of event A1 to AN is exhaustive, means if you take the union, then union will make the entire sample space. So if you take union A1, union A2, union all the way to union A, all the way, okay, so the infinite many, so you will get the entire sample space. So that's mean if that happen, then we say this collection of event is exhaustive event. Okay, and one more concept, we can combine this disjoint and exhaustive, say this partition. Okay, so we say A1 to AN a partition of omega if it is exhaustive and pairwise disjoint. If both happen, pairwise disjoint and exhaustive both and happen at once for a collection of events, then we say it is a partition of omega. So we can visualize this one like this. Okay, so here, this is the sample space, and we can have A1, A2, A3, A4, A5, and so on. Okay, so we can have different partitions, different events with without common area. So that's mean those are disjoint. And if you take the union of these events, okay, so if you take union of A1, union A2, union all the way, you will get omega. So if I draw this one for the two events, okay, if I draw this one for the two events, this will make more sense. Okay, so let's write down this one for two events. So this is A1, and A2. So A1 union A2 will be the entire sample space. Okay. Okay, so now let's see more algebra related with events. So using what we have already defined, concepts, terminologies actually. Okay, so the terminologies are here. Subset of event, or we can say A is containing in B, then we can say it's a subset of B. Equality of events, so then we can say A equal B if and only if A is a subset of B and B is a subset of A. And we can use phi to say phi to say null set or empty set. And we say two events are disjoint if intersection is a null set or empty set. And we say pairwise disjoint means if you have a collection of set, and if you take pair any pair, if it is a disjoint event, then it is, we say it is a mutually exclusive or pairwise disjoint collection of events. And if you take a collection of event and it make this entire sample space after you taking union, then we say it is exhaustive event. And if collection of set is satisfy pairwise disjoint and exhaustive properties, then it is considered as a partition of omega. Okay, so those are the main terminologies we learn. So using those terminologies, now we can find more algebra related with events. Combining the operations of the complement, union, and intersection result in algebra relation on events, assuming B and A1 to A2 are the events. Here are some examples. Okay, so if you take B and B complement and union, you will get the entire sample space. Okay, so we can visualize this one easily here. Okay, so this is omega, and here B, event B, and outside of event B we have B complement. So the orange color part is B complement. So this is B complement. So if you combine, if you take the union of B and B complement, because there's no intersection between B and B complement, so it is like a partition of omega. So you will get entire sample space if you take B union and B complement. So you will get the entire sample space. So here, like B and B complements are the partition of omega. So that's the reason. Okay, and here from this you see that there are no common area for B and B complement. So that's why it's a null set for null set if you consider B and intersection of B and B complement. Okay, now there's a more powerful rule you are going to learn in next slide, which is called De Morgan law. So the De Morgan law says if you have union of complement, so if you have A1 union A2 union all the way to infinity, and if you take the complement of this one, it is same as you are taking intersection of complements. So here, see the pattern. Okay, so that's the easiest way. I'm going to memorize this one. So if you bring this one complement inside, you have to switch the sign. So that's how you can memorize it. So if you bring this complement sign to the inside or the top of each event, so then you have to switch the sign. Okay, so similarly we can extend this one into intersection. So the complement of intersection is a union of complements. Okay, so here A1 intersection A2 intersection all the way to infinity, complement is same as A1 complement union A2 complement union and so on. Okay, so same idea. So if you bring this complement inside, you have to switch the sign. Okay, so that's how you can easily memorize De Morgan law. So sometimes you may use these concepts to calculate the calculate the events inside the calculate the probability actually. Okay. Now let's do one more example related with these concepts. Okay, so let's define two events. A getting a head on the second toss, B is getting exactly two heads. Okay, I think we did this one example. We did this example. Okay. Okay, so we did this example already, but we need to calculate few more things. Okay, so let's complete this event first. So sample space is given. A is getting a head on the second toast. So these are the events here. So I'm not going to repeat this example in detail, but because we did this one already. So getting head on the second toss. So head in the second place. So these are the outcomes. Okay, so a complement is HTH, HTT, TTH, TTP, and B is exactly two heads, H, H, T, T, TH, and THH. And B complement is all the items except these three. So it is H, 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 T, 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 H, T. Okay, so A union B, H, 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 HHT, THH, HTH, and A intersection B, common items for A and B, which is AHTT. Sorry. HHT and PHH. So these are the common items, only two common items for A intersection B. Now I want you to find A union B complement. Okay, so you can use De Morgan law, or you can use just use a set notation and find the values not in A union B. So you have to find the values not in this one, not in this set. Okay, so here let's do that way first. So values in not in A union B. Okay, I think we forget one item here. Okay, so we forget this item. Okay. Okay, so find the items in A union B complement. So that's mean all the items not in A union B. Okay, so HH in the A union B, HHT is here, THH here, HTH is here, THT is here. So those are not in A union B is the last two items. Okay, and one more is missing here, which is HTT. So those are the items not in A union B. So HHT is here, okay. HHT is here. THT, THT, THT is here. HTH, HTH is here. THT, THT. HT, HTH, HTH, HTH here, THT, THT here, HHT, THH, okay, here. This one. Okay, so those are the items in A union B. So that's mean A union B complement should have these three items. Okay, HTT, HTT, TTT, TTH. Okay, so that's how you can find the items in A union B complement. And similarly, now find the items in A intersection B complement. A intersection B complement. Okay. A intersection B has these two items, HHT, HHT, and THH, THH. So except these two, we have write down all the items. So it is HHH, HTH, HTT, THT, TTH, and TTT. So these are the items in A intersection B complement. Now let's see this one as well. Now let's find A complement intersection B complement. Okay, A complement intersection B complement. So that's mean intersection between these two. Okay, so the intersection, I'm going to mark the common items from A complement and B complement. Okay. A complement and B complement common items. HTH. Is there HTH? No. HTT, yes, HTT is there. TTH is here. And TT is here. So the common items are HTT, TTH, and TTT. Okay, can you see these two are equal? This is from, we can say this is from the De Morgan law as well. Okay. So that's what we discuss under the De Morgan law. De Morgan law. Okay. Similarly, you can show this is equals to A complement union B complement. Okay, so if you find the union of these two items, you will get A intersection B complement items as well. Okay, I'm assuming that example help you to understand how to find the events, how to find the items, outcomes in the event, and how to work with event operations. Okay, so next we are going to define the probability idea for the event. So in the event space, the event space denoted by crypted A. So this is not just A. So this is crypted A. Okay. So this is called crypted A, or you can say curly A. So this denote the is a set of all events. So this is the set of all events in omega. Okay, so it's a collection of all events in omega. Then the probability of an event is so the probability is a law, or the probability function is denoted by P of A. So this is the function. So like f of something. Okay, so you have learned f of x. So this is the probability for any function. But when it is come to probability functions, we denote it by P of some value. P of some value here. Okay, so this dot can be any event from this set. Any event from this A. It's a function that's assigning any event in A an unnegative real number. PA is called the probability of an event. So P A is like a function. Okay, so we can denote it like this in the function notation. P is a function from A, crypted A to real number line between 0 and 1. Okay, so after we define probability axioms, this will be more clear. Okay, so for now we can define like this. P is a function from curly A to in the real number line 0 to 1. Okay. PA measure how likely it is the outcome of the random experiment is one of the outcomes in A. So PA says how likely the event A can be occur. Okay. Okay, so later you will learn this part as well. So let's take any event in this collection of A. So then this PA value. So this PA value, this quantity should be between 0 and 1. Okay, so P is a function. Okay, so this is a function. Okay, but it assigns only values between 0 and 1, and its domain is going to be the values in or the events in omega, and its codomain is going to be values between 0 to 1. Okay, so that's the mathematical way we can define a probability of a event or probability function. And so these are the axioms I already mentioned here. Okay, but let's talk about the axioms as rules. Okay, so if we have to impose two axioms actually to the function, then it's make the probability function. So first axiom is all values should be greater than all probability should be greater than or equal 0 for any event. Okay, so your probability value cannot go less than 0. Okay, so the maximum it can be 0. And minimum it can be 0. It's not maximum. Okay, minimum can be 0. And there's a nice property for another property which is called additivity. Okay, so that's mean if you have more than one event, if you want to find the probability of more than one event, so then you can get this summation of individual probabilities if these events are pairwise disjoint. If events are pairwise disjoint, you can find the probability by just adding the probabilities for each event, and this can be extended into more than m number of events, or infinite case. So if you have more than infinite number of events and we want to find the probability and those are pairwise disjoint, then you can take the summation of those events. Okay, so here the meaning here is probability of A1 union A2 union all the way to AM is same as probability of A1 plus probability of A2 all the way to probability of AM. Okay, so this means summation. Okay, so similarly we can expand this one. A1 union A2 union all the way to infinity is same as PA1 plus PA2 all the way to infinity. And the last axiom, which is normalization. So if you find the probability of sample space, it will be 1. That's the maximum probability you can get. Okay. And the small note about probability of null set. So the probability of null set is 0. We can prove this one easily. So this is, I'm not going to ask proofs in this class, but this is a simple proof. So that's why I'm going to provide it. But don't worry, I'm not going to ask proofs in exams or homeworks. Okay. So I can say, if I take union with null set, I will get the same set. Okay. So this is the starting point of the proof. Okay. Now, what I'm going to take is I'm going to take the probability for both sides. So if two events are same, so if you take the probability should be same as well. Okay. And we know probability of omega is 1. Okay, from axiom 1. Okay. So this is true from 1. Okay, axiom 1. So now what I'm going to do is I'm going to write probability of wrong color. Probability of omega union null set is equals to 1. So this by 1. Okay. Now, so now we have but omega and oops, let's write down in different color. But omega and p are disjoint events. That is, if you take the intersection of these two, it is again null. Okay. So that's mean from 2 we can break this. Okay. From 2 we can write this one is same as probability of omega plus probability of p equal 1. Okay. Now we can plug 1 for this one as well from 1. Okay. From axiom 1. So here, now I can write 1 plus probability of phi equal 1. So that's means probability of phi is 0. Okay. So if you subtract 1 from both sides, you will get 0. So I will write 0 here. And I will denote subtracting 1 from both sides. Okay. I'm going to subtract 1 from both sides. And you will get 0 in this side, and p omega is remaining in the left hand side. So that's how you can prove this one, but don't worry. I'm not going to ask proofs. If you don't get this part, that's okay. Okay. And you don't want to memorize or bring this one into your cheat note. And this is denote the end of proof. Okay. So if you have a square with a shaded square or unshaded square, so this implies the proof is done. Okay. 3 more notes and we are done with the today's video. So the second note is suppose you have event A consists of finitely countably finite number of outcomes or infinite set of outcomes. So then you can find the probability of A by adding the probability of each outcome. Okay. So if I expand this side, so this is same as probability of omega 1 plus probability of omega 2 and so on. Okay. So if you want to find the probability of event A, it is same as finding the probability of outcome 1, outcome 2, and so on. And final note, okay, so the last note before the example. So if the sample consists of finite number of equally likely outcomes means we will discuss this one again. Okay. So that means each outcome has the same chance to occur. If that happens, then probability of A is same as number of outcomes in A divided by the number of items in omega. Okay, so this is number of outcomes in A divided by number of outcomes in omega. Okay, so let's complete the last example and then we can stop for the today. Okay, so I think the video is little bit larger than 1 hour, so that's okay because we are done with the entire topic. Okay, so let's discuss this example and for this video. Consider an experiment of rolling a pair of four-sided fair die. What is the probability of a sum of the roll is even, B is the sum of the roll is odd, C is the first roll is equals to the second roll, D is the first roll is larger than the second roll, E at least one roll is equals to 4. So we have to find the probabilities of these events. Okay, and it says we are rolling a fair dice. So fair dice mean those are equally likely events. So if it is equally likely, we can we have to find the items in A and divide it by total sample size. Okay, so first of all, we have to write down the entire sample space. That's little hard because we have to write like this. Okay, 1 1. So 1 1 means first die is 1, second die is 1, 1 2. First one is 1 and second one is 2, and so on. We have to write down all the sample space. That's take more time. So what we can do here is we can visualize the sample space using different form. Okay, so see this form. Okay, I'm going to use 2 axes. X-axis is for first dice and y-axis is for second dice. Okay, and here I'm going to denote 1, 2, 3, and 4, and here 1, 2, 3, and 4. Now, without listing all the sample space, I can quickly denote the entire sample space like this. It's 1 1, 1 2, or 2 1, 1 3 1, 4 1, or we can say 1 2, 1 3, 1 4, 2 2, 2 3, 2 4, 3 2, 3 3, 3 4, and here 4 2, 4 3, 4 4. So here it denotes the all sample points. Okay, now let's calculate the probabilities one by one. So sum of the roll is even. Okay, here the roll should be even, so we can list all the outcomes. Okay, sum is even. So if you get the sum of the two values showing in the dice, you should get the even number. So the outcomes are 1 1. If you add this 1 1, you will get 2, which is even. Or 1 3, 1 1, and 1 3, you will get even numbers if you get the summation of 1 plus 3. And similarly, you will get 2 2, 2 4, 3 1, 3 3, 4 2, and 4 4. So these are the all outcomes in event A. Now we can find the probability of A using, because these are fair dice, so it's equally likely events, we can do PA is equal NA over N omega. In A is number of items in A, which is 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 events in A, and total number of events in entire sample space, which is number of points in this graph, which is 16. Okay, so it is 1/2. So when you are putting your answer, you can put the answer in simplified fraction form, or you can put in the decimal form. Okay, so those are those. This is the probability of event A. Now let's find the answer for B. Okay, I'm assuming this makes sense. So if you have any questions, please send me an email or visit my office hours. Okay, so here B says, so you can list items in B. B says the sum of the roll is odd. Okay, so you can list the item here and find the values. Okay, but here we can use something else. Okay, so that's to you. You can list these items and find probability of B. But what I'm going to do is I'm going to use something different. Okay, so if this is odd values and this is you list even values. So if you got summation of odd and summation of even, you will get the entire sample space. If you got A union B, you will get the entire sample space. Okay, so if I take the probability of both sides, you will get this equation. And from 1, we can say, from axiom 1, we can say probability of A union B equal, and this is 1. Okay, so from axiom 1. Now see this one as well. See this property of A and B. If you get the intersection of A and B, it will be a null set. So that means A and B are disjoint. If A and B are disjoint, we can break this one into 2 probabilities. So this means probability of A plus probability of B is 1. So we know probability of A is half. So probability of B also going to be half. Okay. So still you are free to use listing items in B and then find the probability using the equation, or you can use this trick to find the probability of B. That's easy. Okay, so C says the first roll is equals to the second roll. So I'm not going to list item, but I will denote it in different way. First one is same as the second one. So these are the values. So we don't want to know the exact outcome. We want to know how many outcomes in the event. That's the only thing we need to know. So it is 4. So this is the event C. Okay. So probability of C is NC over N omega, which is 4 over 16 is 1/4. Okay. And part D, okay, so part D says the first roll is larger than the second roll. First one is larger than the second roll. Okay, so first one is always larger than the second roll if you consider this set. First one is larger than the second one on these items. So this is D. Okay. So D, probability of D equal ND over N omega, which is 1, 2, 3, 4, 5, 6. 6 over 16, or which is if you divide by 2, it is 8, and here 3 8. Okay, and the last question is hidden, so it's in the wrong place, E. Okay, let's use different color, E. Okay, probability of E. Okay, at least one roll is equals to 4. At least one means both can be equals to 4 as well. Okay, at least one is 4. Okay, so this is 4 and this is also 4. At least means first one should be can be 4, second one can be 4, both can be 4. So that means these are the items in E. Okay, black color one. Okay, so here we have 1 2 3 4 5 6 7 7 9. Okay, so the probability of E is 7 over 16. Okay, so let's write down the equation and then plug NE over N omega, which is 7 over 60. Okay,